So for the power converter, you will need two books. The first one will be the one from Power Electronics, for sure. This one, Power Electronics Converters Model Linear Control. This one will cover the way they model the power electronics, like a power converter, HVDC, and some use case. And the second one is for the fuzzy. This one from this one is the one called fuzzy control system design and analysis of Tanaka. You don't need to read everything, just read some part of this. So for the one from Power Electronic, we only need to first to have some idea about average model and general like average model, switch model. That part will be covered by another lesson, but not this one. For this lesson, we focus on the fuzzy model, the fuzzy modeling methodology. So imagine you have a state-space system like the previous lessons, but in this case you have the state-space matrices are the functions of the state and the input of the system. So this matrix chain according to the state and according to the input is not a constant anymore. So from this, how can we design a controller? Because the state-space linear model is the methodology is only for the constant time invariant matrices, but not this one. So the fuzzification is a methodology to convert this model with this matrix into a set of state-space system. They call it like a set, for example. A set they call it is a rule. For example, as rule I, you have a state-space system like this. But in this set, in this rule, this matrix will be constants. So you can imagine you have this one is the physical model. So you can you try to model this physical behavior of your system by a set of linear time invariant system, state-space system. So it's like a function, a function of your. You try to establish a function from a set of time invariant state space system to your physical system. It will be a little bit difficult to tune directly to fuzzy, but just follow along. So we should and just focus on the continuous fuzzy system to have some ideas about fuzzy first, and then you can go to discrete or something like that. So you okay, so first you just need to know some instruction. Need to know this. There's different kind of this system, but for power system, just focus on this one. So they call it the Takagi-Sugeno fuzzy model. Another one they call it Madanime, but that one is not suitable for power converter in particular. You can use it, but it's not efficient. So how to control the function or the rule as we mentioned before. So there's two main ideas like this. Actually, they have a couple ideas, not just the two methodologies, but this one is these two are the best one for now. They have another one called a multimodal, but if you want, you can look at them. They call it multimodal. So for the first one, they call it fuzzy identification. It's somehow like artificial intelligence. Not exactly, but somehow like that. So they use a black box with the without model. So the identification, the structure of the system, the parameters, or something like that. It depends on some particular cases. And that when you have the data and you already know somehow the structure of your system. For example, you have something like this, you already know there's some states, how many states, how many input, and you can use the input and output the data to determine the matrix A, B, C, D in a function of states, or even you can determine at a set of rules like this one. So in some condition, you will have a constant matrices like this. You change some condition, you have another one, and that's all for the identification methodology, but for our case we will focus on the second methodology. So you fully understand your system, so you can write you can draw a state space or something like this, but you understand, you already know how to express, how to require your matrices as a function of state, like this. For example, you have a model of your converter, inverters, or something like that, and then you can write some. Okay, so for the second methodology, you have to fully understand your system. This means that you already have something like this. So when you have something like this, you have a chance to create a set of invariant state space system. Exactly like what I mentioned before. That methodology, they call it it is based on the so-called set nonlinearity. So the idea of set nonlinearity is for example your matrix A, here matrix with let's say you have 4 elements. So there are 2 elements, depends on the state or depend on the input. So those elements will be nonlinear set or set the nonlinearity. So first we go to example, it's easier to understand. So you have a physical system like this, a nonlinear system like this one, and you will describe your system like this. Here is a system without input or autonomous system. So you have this one and this one will be depends on the state, the 2 states of the system. So they call it here, they put it Z1 and Z2, and they call it the nonlinear systems because it's not linear. It depends on the state. It's not constant. So come back here. So this, for example, here you have a nonlinear set called fx, and you understand that, or you assume that your state will only act in a range. The physical system for sure. You cannot have a state go to infinite value or something like that. You have to have a range of state. For example, the temperature in your room or the speed of your car. Here and here. You have the mass. So for sure you have the maximum value your function, your nonlinear sector, and the minimum is the same for both sides, here and here. So by drawing two lines like this, you ensure that your nonlinear sector will only vary inside the range of between the two straight lines, A1 and A2. So for sure, the nonlinear sector will be a function of the two values, but you have to find a way to express that. And in the end, you will have, by doing this, you will convert your nonlinear sector into a function of a set of two, you see, a set of two linear sector. So your matrix A will become a constant in some conditions. Okay, so here, come back to this system. You have this one and this one, and here is set an assumption that your state x1 and x2 will vary only between -1 and 1. So you have maximum value of S1 will be 1 and min will be -1. The same for S2. And here is the point, they call it the rule. So here the point, they call it the rule. Okay, it's a bit hard to understand, but will be a function. So you see a maximum value and a minimum value, a combination. But you have to find this function m1 and m2. And from this, you can recover your nonlinear sector. The same for yes 2, the maximum and the minimum. So it's here is the set it equal to 1 because it's a 100%. Like for some case you have m1 will equal to 1, and so it will be the maximum. Some case you have m2 equal to 1, so it's just 1 will be the minimum. So here the way to convert it, so you convert it from the real value of yes. So it's actually it's a function of state. The two function will be a function of states because the knowledge set there will be a function of state. So okay. So in the end, you will have the four function will be a function of state, and by observe the state, you can calculate this function. So now you have a knowledge sector become a set, a combination of a set of two linear sector, which is the maximum and the minimum values of that nonlinear sector. So follow up, So they call it. So now you have, for example, you set it positive, but you can set it equal to the maximum or something like that. It's just a name. So actually you set up if z1 equal to 1 and z2 equal to 4. So you have this one. And the second will be the same. Because you have here you have 2, and for the second one you have 2. So in the end you have 4 rows. Like this. And you have 4 matrices from matrix A, A1, A2, A4, A3. And here the trick. So from that you can recover your system by a setup. You see a setup function of matrix A. Set up a linear matrix, linear here. And why is we have this? For the first one, H1 will be this one. Depends on the rule you set here. It's maximum and maximum. So it will be N1 and N1. You see? The same for 8, 2, 3, 4. So just follow this example, you understand. So now apply to the buck boost converter. So I hope you have to first you have to understand this converter. Otherwise you have no chance to follow. So basically it's like this. So it's just a converter to change the voltage depends on the duty you set here. So physically you have a system like this one, and as you can see here you will have a nonlinear system since you have the term Vc multiplied by U. So if you choose the state Vc and you set that the matrix A will contain U, or the same for the if you set U, the input here, yes, the input here, so the matrix B here will contain the state V minus Vc. So this is what I choose. Will be a state. So the matrix B will contain the Vc, as you can see here. The same for the V, but for the derivative of Vc, we don't have nonlinear system, but for derivative of the current, you have this one. This one. Vc. And now let me change this again. And it's the same for the you still have for the derivative of Vc, you still have here, IL. So you have two nonlinear sector, this one and this one. So you have 4 rows. So the matrix A will like this. So you have this one. Matrix A will be constant, but matrix B will be a set of constant matrices. This one, this one, this one, and this one. And the function to you see, it could be this, the setup. Matrix B will be a setup from matrix with the function m1 and n1. You see, m1 and n1 will be calculated from the state and the range of state, as I said it here. The same for m2 and n2, n1 and 2. So now we can compare. So here it's actually I compare between 3 average model, switch model, or you can call it detail model, and fuzzy model. But for now, you just focus on the fuzzy and the real model. The real model, which is the IL, average model will be ILA and fuzzy. But just ignore the ILA. Just focus on the fuzzy and the detail model, which is IE. So this is the behavior of the system. So as you can see here, for the real model, the fuzzy model can okay. Okay, so the fuzzy model. Okay, so here it's clearer. Can spread the behavior of the system. Not 100%, but very close to the model. So by using the fuzzy modeling, you can spread your model by a set of linear function, a linear sized by, and you can use the linear control system design for here to design a linear system to create again case, for example, the feedback control to control your linear system, your nonlinear system here. So that's the trick. So you use linear control, but you can control the whole nonlinear system. This is much easier and is a simple solution. For example, our converter, you have many states. For like when you build a real project, you have to use the MCU, and for some complicated control like MPC, model predictive control, or something like that, you have the cost of control. But with this, you just need some memory to store your gain k, Even here you can put the static k, but normally you only need the gain k for the static gain k for this, and then you can call it by observe the state. You can convert recover your behavior of your system, as you see like this, by a set of linear system, and based on that you can control the system. That will show you next time.